Hello friends, welcome to class 10 lecture on buckling analysis of the course FE of Aero structures. So in this class I will be speaking to you on the buckling theory first to give you a brush up of the theory, and then slowly we will be moving into the pattern demonstration. First, to start with buckling. So buckling falls under the category of instabilities. When I say instability means the structure is not in a stable position to support any given loading. That is called instability. So, in order to understand instability, you have to understand what is stability. Stability of yes, instability is exactly the phenomenon is opposite to the stability. Stability is nothing but it is the ability of a structure that is able to support any given load without experiencing any change in the equilibrium configuration or the shape. It might be a deformed shape or deflected shape. To give you a very simple example to this, imagine a column and you are applying a force. Suppose you are designing the column and you say that a certain amount of force it can take. After designing, suppose you are testing it, and then if the column fails without any taking what is the desired amount of load, so definitely that means there is some problem with the structure or with the design parameters considered or with the support conditions considered. It might be any type of problem. So one has to understand that this buckling phenomena is directly related to its stiffness of the structure. So stiffness of the structure is related to its equilibrium configuration and the deflected shape. So this phenomena of instability, which is the tendency of the structure to change its equilibrium configuration all of a sudden, or the shape of the structure under a loading, is called buckling. So buckling could occur either by compressive loading as in the columns, but on your flat plates or in the aerospace structures on the wing skin or on the fuselage skin, it can occur due to the combination of axial loads, or it's a combination of axial and shear, combination of when I say combination of axial, it is bidirectional axial, combination of axial and shear, combination of shear and bending, combination of axial shear and bending. It might be various different combinations. So what happens to the structure when it is under buckling? It undergoes a severe deformation. So there is a loss of stability. It no longer can support the loading, and sometimes what happens, there are structures that exhibit post buckling phenomena. When I say post buckling phenomena, that means even after the buckling it might continue to take certain amount of load, and then ultimately it will fail. It will completely deform, or completely it will fail. So you can see the structure which is undergoing buckling, so how it has deformed, and this deformation is called the buckled form, where this is also called as the mode shape of the structures which is undergoing the buckling. So coming to the aircraft structures, those are mainly beams and very thin structures in terms of skin panels. These undergo buckling in a very different fashion compared to the classical column, they these kind of thin structures, they sometimes they undergo only the web buckling, sometimes the web panel, web of the spots or webs of the ribs undergo buckling, or sometimes the flanges undergo buckling. So whenever there is a local buckling within the flange or within the web, then it is called crippling. That means on some portion of the structure buckles locally, it's called crippling. But when the overall structure undergoes buckling, then it is uh, a sort of instability to the structure. So first of all, the structures are designed in such a fashion that it doesn't undergo any buckling, like all the parameters have been taken into consideration, all the proof load factors and the ultimate load factors have been put in place, just that it does not undergo into the buckling scenario. So if I go to the next slide, I can show you that whenever the load is applied and whenever the load is increased, there is a point called a bifurcation point on the structure. Bifurcation point is nothing but a point where the structure changes its equilibrium configuration. It can be a change in shape, or it can be a change in the way it deformed, and it's continuing to support the load. So this bifurcated path represents the change in the equilibrium configuration. After that, it trying to support the load, and then it when the when the structure doesn't change the configuration but still it continues to support the load, it will be limit point. And once the limit point is reached, it is the critical buckling load where it has reached. Finally, it can undergo a change in configuration, or it might fail. So there are two types of buckling, which is the bifurcation buckling, where in the middle it immediately changes the path, and other one is limit point buckling. And also there are linear buckling and non-linear buckling. So linear elastic is when the buckling stress stays critical buckling load and the buckling stress stays within the elastic region, then it is linear elastic. And other than that, it's non-linear elastic. And sometimes when the non-linear materials have been used, or when it goes to the plastic region after the elastic, then it becomes non-linear elastic. So what is bifurcation? Bifurcation, as I mentioned, it is a different equilibrium configuration after the initial buckling. When they say that after the initial buckling, it is like it might it continues to take the load even after the buckling. It might be a post buckling scenario where it continues till it fails completely, when the structure is completely failed. So before we get into the linear and non-linear elastic buckling, I would like to show you the theoretical solution for your column buckling. So imagine a column that is on one end it is fixed, clamped, and other one it is free, and then a load is applied. So this is what we uh, derive in the strength of materials, or the classical formula for a critical buckling load for a typical column, something like this. Only thing is the effective length of the column will change depending on the boundary conditions. The same column can be represented using the differential equations, and then we apply the boundary conditions to get the non-trivial solution, and then finally substituting the non-trivial solution and back into the governing equation, we get the critical load. So whatever we see the non-trivial solution to the equation, which is the lambda. Lambda is called the eigenvalues, and x parameters will be deflected mode shapes. So here, if you look at the critical buckling load is being derived, and then it undergoes, as I mentioned, it undergoes the buckling phenomenon, the structure, which is in this case it is a column. So you can see there are different mode shapes. There are only three mode shapes that have been extracted. On the first mode shape, it deflects like a semicircle, and second mode shape, you can say the wave pattern like a sine or cos, and then third, the wave patterns have been increased. So there are different wave patterns or different mode shapes that your structure can undergo in buckling. So mostly the buckling will, as I mentioned earlier, it depends on the slenderness ratio and also on the flexural rigidity of the column. So buckling will start initiate with the on the plane which has a minimum moment of inertia, and also the buckling can be increased. The buckling load, the critical buckling load can be increased when you are bracing the column at its ends. When you say bracing, it is like clamping the ends, fixing the ends. So this is a typical buckling solution for a column, how the buckling loads have been calculated, and how the you can visualize there are different for different boundary conditions, for different support conditions, how the buckling load will vary. So the same physics or the same fundamentals will be used on the 2D plates when analyzing for buckling. So instead of 1D equation, they will be using the 2D plate equation and applying the boundary conditions, and then solving the characteristic equation to find the eigenvalues and eigen vectors. Eigenvectors are nothing but the mode shapes, which is the deflected wave patterns, how the plate undergoes deflection and how the load within the structure is being resisted using the wave pattern. So going back to the linear elastic and non-linear elastic buckling. Linear elastic buckling is, as we saw the couple of examples now, which is the column uh, and plate, as I mentioned. So those are nothing but the linear elastic buckling, which are eigenvalue buckling. So it predicts the eigenvalue buckling, predicts the theoretical buckling strength of your structure, and then buckling loads are then derived with the for each buckled mode of the structure, and the primary output from the buckling analysis in a set of tool is the buckling factors. So what we get from the FE tool is a typical buckling factor. To we have to multiply these factors to the applied loading to get the to understand the loading at which the buckling would initiate, buckling would start. So similarly, nonlinear buckling would uh, what happens is it's similar to the nonlinear static analysis. It applies the load in a small increments of time, or sometimes what happens, the if the structure has the nonlinear material, then it falls under the nonlinear buckling category. So it is, other than that, the rest is similar to the linear elastic buckling. It computes the FE tool computes the buckling factor. So you have to multiply the buckling factor to the applied loading to get the critical buckling load. So before we get into the pattern demonstration, so I would like to speak to you on the important considerations of the buckling analysis, especially through the finite element method. So first one is the primary output of the linear buckling analysis would be a set of buckling factor. So these buckling modes and the associated load factors will be the primary output for any FE tool for any for the buckling analysis that been carried out. So buckling load factor is nothing but a number that will be applied to the that will be multiplied to the applied load and to get the buckling load magnitude. So sometimes what happens, sometimes it will be divided based on the particular FE package. There are for example FEMAP, there is a FE tool. What happens is when the buckling analysis has been run, so it gives the buckling load factor that we need to divide by the upload loading in order to get the critical buckling load. So it's depend on the coding or how do they internally return the max within the FE tool, how to compute the buckling load factors for the structures. So the buckling mode represents the shape of the structure that is undergoing the buckling, that is whatever we have discussed now, when it undergoes a wave pattern or when it undergoes a alternating pattern, those buckling modes. So and the user might extract different buckling modes based on the requirement. You might go for first five buckling modes or first 10 buckling modes based on the whatever it is the requirement or to whatever is the goal to which they are designing the structure. And then the if you look at the buckling analysis, finally it is exactly not exactly, I would say it is something similar to the modal analysis concept of the modal analysis, where we calculate the again the mode shapes and the model values, and then finally the deflections, forces and reactions all correspond to the normalized buckled shape of the structure. So whatever you get on the output as a support reactions or something, that will be uh, that will be corresponding to the structure that underwent the buckling, not the initial structure which is before buckling. So one must run the nonlinear analysis in order to understand how the support reactions, how the variations in the support reactions change with time. Suppose you're running a nonlinear analysis, and then with respect to time, at time step t equal to 0, you applied some loading to the structure, and there might be a different support reactions coming from the structure, and once it underwent buckling, and at time t equal to after 10 seconds or 15 seconds, there might be a there might be a variation in the support reaction, because the whenever the structure undergoes buckling, as the configuration changes or when it gets deformed, the distribution of the load within the structure obviously changes. So there might be a variation in the support reaction. That's what this last point meant. So now let's quickly look into how the buckling is computed in some of the industries using the empirical methods. So usually in the aircraft industries, when the people want to do a preliminary design or for the preliminary certification, when they want to do an hand calculation of the buckling analysis, they go with the empirical formulas that is derived based on the theory of elasticity. What you can see here is a simple plate that is under the action of compressive load. So for any plate which undergoes buckling, one of the important parameter is the aspect ratio of the plate, which is A by B. So based on the A by B, there are different on based on the different boundary conditions. You can see on the right there are different boundary conditions here, which is clamped, simply supported, and there are various combinations. There are only simply supported and it's fully clamped based on the boundary conditions of the edge, and there are various different tested graphical data are available to select the buckling coefficient Kc, and then there are also there are some knockdown factors that are used for the plasticity effects to consider the plasticity effects, such as plasticity reduction factor. What you can see over here is an eta, which is the plasticity reduction factor, and then there are also some in some of the industries they use the reduction factor, knockdown factor for cladding reduction factor, and then finally they compute the critical buckling stress, um, which is then used for calculating the reserve factors and margin of safety against the applied buckling stress. So now, before finally we get into the demonstration, I'd like to show how the for a simple column, how the Nastron gives the output. So you can see the simple column that is being idealized as 3 rod element, apologies, and then it is acted upon by a compressive load at the end and clamped at the other end. So here you can see the Nastron BDF file, which is the input file, and then there is an eigenRL command that represents the eigenvalue extraction, which is for the mode shape for this column. I will get into the detail of the eigenRL in towards the end of the presentation. I will go through what are all the Nastron commands that is required for buckling separately. So at the moment, let's understand. We have a column over here with a set of dimensions. We have the geometry, we have the material properties, and we have the geometrical properties defined. And I am running the buckling analysis within Patra, column buckling analysis, and then what I am getting over here is this is the output from the Patron, Nastron. So what I'm getting is the eigenvalue. Uh, Eigenvalue is the buckling load factor. So this buckling load factor will be then when I combine to the, I'm going back to the slide. It's combined and the buckling load factor is multiplied to the applied loading. Applied loading is 1 Newton force that is being applied. So you can see the vertical negative load which is acting in the downward direction, 1 Newton. So when I multiply, I get the critical buckling load. This is what I mentioned earlier, that Nastron Patron gives the buckling load factor that needs to be multiplied to the applied loading in order to derive the critical buckling load. If you calculate the uh, critical buckling load for this same column with the classical solution, you will get the same 32 point something 32.17 as the critical buckling load.